Let's start now. Well, I'll just start here. So welcome to the annual Mars Luncheon Society. These are always a lot of fun. And there's always a lot of things going on Mars. And we've had several of these, I'd say 7 or 8 of these in the past with Steve Squires, many with John, and many with a variety of other people. And because the space element of the Luncheon Society covers a lot of tracks. It could be Rusty Schweikert on the human element of spaceflight. Jill Tarter has joined us on several occasions to talk about SETI. Like I said, we had Doug Osheroff and Scott Hubbard going over the Columbia Accident Investigation Board. And there was one great luncheon that we had in 2007 with the ASE, which had Scott Carpenter, Wally Schirra, Alexei Leonov. I mean, just this eye-popping collection of space pioneers. But the thing about Mars that's fun is it's happening and it's now, and that we're getting closer, I would say, to the idea of sample return, which is extremely important, which I think is going to be a big piece. I'm sure John will talk about this, but more importantly is that NASA has taken the long view. What started as an incremental testbed program with Sojourner has now grown to this amazing, these amazing rovers that are about the size of an SUV with a Perseverance and Curiosity. But the star of the show on Mars right now is not Perseverance as much as it's Ingenuity, which is a small test bed of a helicopter, which I think will be the future of stuff. But I don't want to take away John's thunder. For that, John, take it away. I'm going to put if you're not on mute, let's go on mute, and then we can get ready for Q&A after. So John, you're up.
All right. Bob, thank you very much. Welcome, everybody. It's great to be back here for the Luncheon Society. As Bob mentioned, I've given this talk a few times before. Of course, I've updated it with some recent results. What I want to do today, though, is maybe just take a little bit of a different spin on this. I mean, some of you who have seen me speak before will see some familiar slides, but I want to talk about how our perspective as Mars has changed since the beginning of the space program. And a perspective from the human point of view is how we look at the planet and how we see it. And this will have something to do with our technology improvements, as well as our human adaptation about what we think of Mars. And then I'm going to include a little bit about the iconography of these missions, maybe a little lesser known stories about some of the vehicles as we go through this epic adventure. So I'll start as I often do and remind us of what we used to know about Mars. And this image that you see here is a ground-based telescopic image. This is something that you might be able to do in your own backyard with a 8 to 12 aperture telescope during opposition when Mars is close to the Earth. And you would see this fuzzy ball, and you would notice that it has polar caps, and it would have surface features, and those features would change from season to season. We know that Mars is tilted 5 degrees, very close to the Earth's 23 1/3 degrees. So Mars, like the Earth, has 4 distinct seasons. And those surface features I mentioned would seem to change in correlation with the seasons. And so this led the early astronomers like Percival Lowell to make these claims of life on Mars, and that they followed a seasonal cycle. And they had many of the same challenges that we as humans here have on Earth with our changing environment and how we adapt. But it wasn't really until the space program that we got our first close-up look, a change in perspective of Mars. And that was in 1964, actually in 65. We launched the Mariner 4 spacecraft in 1964 and arrived in 65. And this is one of the images from the Mariner spacecraft. And you could see craters, as you might expect, because of the impacts that early planetary bodies experience, much like our moon. But we know Mars has an atmosphere, and so these features are different, eroded and weathered. But this is, once again, was at the limit of what our technology could do. And it always resets what our baseline was. Just the previous slide was the telescopic image of Mars. And now we see the surface. And now we have our next set of questions about the surface of Mars and about the planet as a whole. And so Mariner 4 began this systematic exploration of the red planet by NASA, and followed by Mariner 6 and 7, and then Mariner 9. And this is an image taken by the Mariner 9 spacecraft, which went into orbit around Mars, not just a brief flyby, but actually a sustained presence staring down at the surface. And these are teardrop-shaped islands with some craters in them. And this, of course, is very reminiscent to teardrop-shaped islands here on the Earth that are carved by flowing water. So you can imagine water flowing from the left to the right in this image, forming these islands. And so this is, dramatic evidence of a putative water history to Mars. But we know today Mars is very dry and barren. And then in the mid 1970s, we really upped the exploration of the planet with the two Viking missions. There were two Viking orbiters, Viking 1 and Viking 2, and two landers that fixed down onto the surface of Mars. This is the introduction of color imagery to the exploration. And you can see this thin, tenuous atmosphere of Mars. You can see the eroded craters, indicative of some sort of weathering that's going on the surface of Mars, some sort of erosional processes. So it's not static like the moon, it's more dynamic like the Earth. But yet we don't see oceans, we don't see forests, we don't see luncheon societies gathering to have smart talks. But as I mentioned, the Vikings had two landers, and here is one of the Viking landers touching down on the surface. Now, Viking was intended to search for life on Mars, and there were 3 experiments on each lander. They each had 3 control experiments. They took soil samples from the surface, they had a robotic arm. They introduced those samples into the 3 experiments, and essentially they were looking to see if they could make something grow on Mars, to see if they could find any indication of metabolism on the surface of Mars. And even to this day, 50 years later, there's still, controversy about the results that Viking collected. But I think the general assessment is that the Viking found no conclusive evidence of life on Mars. And we had put so much into looking for life with the Viking missions that the sort of null result we got kind of threw a wet blanket on the exploration of Mars. And it wasn't until 20 years later, 2 decades, that we returned to the exploration of Mars. And the first was with the Mars Pathfinder mission, which was not a scientific mission. It was an engineering demonstration mission. It's meant to be low cost. It was sort of the mantra of faster, better, cheaper that some of you might remember. And it was very innovative. And it path found several critical technologies. One was a landing system using the airbag system, entry, descent, and landing. And the other is a freely roving robotic vehicle. And you see in this image here, you see Sojourner, this little 6-wheeled, solar-powered, radio-controlled rover. It was about the size of a microwave oven. And it couldn't travel any further than what you sort of see in this image, about 10 meters or maybe 30 feet from the lander, because it was dependent on the lander for communication. And when it comes to rovers, size does matter. The bigger the rover is, the more equipment it can carry, the farther it can go, and the larger the obstacles it can traverse. Not shown in this image was one of the things that NASA kind of slapped JPL's hand with. We had put a JPL logo on the side of the lander instead of a NASA beep ball. And they said, don't do that. And so we had to make sure of our decoration or decaling going forward from here. But you can also see that JPL doesn't always listen to NASA. Anyways, Pathfinder was a tremendous success. It really drove these technologies that became essential to future exploration. But it also marked this return to the exploration of Mars. So while Pathfinder was on the ground, we had orbiting above Mars Global Surveyor. Now, I don't have a picture of the spacecraft, but I want to show it's some of the data the Mars Global Surveyor collected. And this is altimetry data. And as its name implies, it did a global survey of Mars. We kind of got burned with Viking by being too narrowly focused on the search for life, or life as we understood it in the 1960s and the 1970s. And so now we've widened our perspective, and we're looking holistically at the planet Mars. And what you see in this color-coded image of the hemispheres of Mars is topography. Red and white are high elevation, and blue and purple are low elevation. And you can see some very striking things right away. First is you see that the northern hemisphere of Mars is not only very low, but also very smooth. And the blue coloring makes it very suggestive that perhaps Mars had a great northern ocean at one time. You can see these great channels that are suggestive of flowing rivers that might have fed a great northern ocean. Now, this is, of course, subject to speculation and investigation by the scientific community. There are many scientists on either side of this question about a northern ocean, but clearly there was water on Mars at one time, and how much and what happened to it are the questions that we're trying to investigate by investigating the planet with further exploration of the planet. But Global Surveyor gave us this really wonderful global data set, which became the basis for further exploration of Mars. And so to answer some of these questions, we wanted to go back to, we wanted to go back to Mars, and that was with the Mars exploration rovers, Spirit and Opportunity. And here you can see one of the rovers here. They're identicals. There are only these tiny subtle differences between the two rovers, so I can't tell you whether this is Spirit or Opportunity. One would have to actually peek inside the rover to distinguish them. But you can see it's a larger rover. I mentioned earlier, size does matter. Essentially, the obstacles that you can traverse are of order of the wheel size. So these are 25 centimeter diameter wheels, so we can go over rocks about 25 centimeters. So, Bob, that's like taking your Lexus and with your 30-inch diameter wheels and driving over 30-inch rocks. I'm not sure you've done that, but you could. Further difference with these rovers is not only they're larger, but they carry everything with them. Whereas Sojourner was dependent on the lander for communication, these rovers can directly communicate to Earth or communicate with orbiting spacecraft. And that's a significant capability that we really exploited with the exploration of the surface of Mars with rovers. It carries a suite of instrumentation. You can just make out on the front of the rover, there's a robotic arm that's stowed up underneath about the size of your own arm. And so this allows us to touch the surface of Mars and to sample it, or to be metaphoric, to taste the surface of Mars. So Spirit and Opportunity are kind of like field geologists. If you think about what a field geologist does, and Dave DuMarais knows exactly what that means, is that you walk around and you use your vision. And so here you can see we have cameras up here on top of the mast that are just about human height that survey the ground around us, drive up to them and get down on our hands and knees, if you will, deploy this robotic arm and take samples. A geologist will take out their rock hammer and crack open the rocks and pull out their hand lens and look inside these cracked open rocks to look at the fresh material, because a rock is like a book. You can't judge it by its cover. You want to get inside. And we have a tool called the rock abrasion tool, which allows us to grind inside the rock to do equivalently the same thing. So Spirit and Opportunity were set up to do field geology on Mars. And this was really remarkable because it was taking that next step in the exploration of the planet, not only to look at it from a distance, but actually to traverse it with your own feet and to look with your own eyes. So we used the entry, descent, and landing system to get us onto the surface of Mars. And here we are. This is the day after we landed. So we landed on January 4th, 2004. And that day is significant in that it marked the beginning of the uninterrupted, sustained exploration of the surface of Mars. So we have had active exploration assets on the surface of Mars ever since January 4th, 2004, up until today. And so that now marks, we're coming up on, 2 decades of sustained exploration of Mars. Now, when we landed, we didn't have any idea that we would have this kind of legacy. We were designed for 90 days on the surface of Mars, 3 months, and a traverse capability of only 1 kilometer, which at the time was a significant improvement over the technology demonstrated by the Pathfinder mission, where the rover was only designed, Sojourner, to last a week on the surface. And so here we're baselining 90 days and 1 kilometer of exploration. And so there was lots to do. And we did explore, but we lasted longer than those 90 days. And we lasted long enough to enable a sustained exploration. Now, one of the things that is a common human activity to do is to take a selfie. And we've taken a number of selfies. And this is a selfie of opportunity on the surface. And I wanted to take this opportunity to talk a little bit about the how we invest our vehicles with our own characteristics, not only anthropomorphizing them, but adding in the little things that have nothing to do with scientific exploration, but are part of human iconography, I'll call it, if you will. And then you'll notice we didn't pay attention to NASA. Up here at the top of the rover on the lead solar panels, you can see there is a JPL logo. But we did include the NASA meatball as well. And, okay, we didn't quite pay attention to what NASA told us not to do. There's also another hidden logo on the forearm of the front steering mechanism of the rover. But you may also know that we have a microchip on the rover. It's hard to see, and it's one of these little dots back here. Actually, I'm sorry, it's this dot right here. And that has signatures of thousands of people that sent their signatures to Mars. And this is something we've done with all our missions. So all our rovers carry signatures of thousands of people from around the globe who want to share in putting their mark on the red planet. So the rovers explored Mars. Spirit lasted more than 6 years, and Opportunity lasted 14 and a half years on the surface of Mars. And we were able to traverse many kilometers. And importantly, we were able to go back in time. And this picture is one of my favorite because it shows Opportunity on the rim of Endeavour crater, which is this large, highly eroded crater that dates back to the earliest epoch on Mars, what we call the Noachian epoch, in which Mars was warmer and wetter. And you can follow the rover wheel tracks all the way to the distance here. And you might also ask, you see this regular pattern in the rover wheel tracks. Well, when the rovers were sent to Mars, they were sent inside a lander, and they were bolted to the lander through their wheels. So there's this fixture in each of the wheels, it's a little hexagonal pattern, or almost like a waffle-like pattern. And as the wheels rotate on the surface, they imprint that pattern into their wheel tracks. It turns out this was a great thing to do, because we know the distance of one wheel rotation, it's just pi times 25 centimeters. And it's like laying out a ruler on the surface of Mars as we traverse. So when we look at these images, we can very quickly interpret scale set out in these images. Here we are at the highest point along the rim of Endeavour crater. You can stare to the horizon there and see the sort of false color turquoise blue haze that fills the interior of the crater. And you can see the end of the robotic arm in which we've raised the rock abrasion tool. And there's a flag on the side of the aluminum shield on that rock abrasion tool. And there's a story with this, in that the rock abrasion tool was built by a company called Honeybee Robotics. And at the time, Honeybee Robotics had a facility on Manhattan in New York. And they were in the process of building the 2 rock abrasion tools for each of the rovers on September 11th, 2001, where the World Trade Center was attacked by terrorist actors. And the team was very affected. They, of course, were there the day that the terrorist attack occurred, and had were greatly affected by it because they too had to be evacuated out of Manhattan on that day. Fortunately, none of their personnel were injured by the events that day, but like every New Yorker and every American, we were all deeply affected. And so they approached the city of New York, the state of New York, and the Port Authority of New York, and they asked if they could recover a piece of material from the World Trade Center site. Specifically, they asked for some pieces of aluminum. And they were granted that permission, and they fabricated those aluminum into the shield that you see on the rock abrasion tool right here. So out of the rubble of 9/11, they built part of the rock abrasion tool that traveled to the surface of Mars. And originally they weren't given permission to do this because we weren't sure of the political optics of flying to Mars, a piece of rubble from the World Trade Center site. And at the last minute, the science team swapped out and put in the shield. They had another shield that was just a industrially produced aluminum from a vendor, but they swapped out and it flew to Mars, and here it is. And so it's another aspect of the humanity that we put into our missions, exploring the surface of Mars. But both rovers had a phenomenal career of exploration on the planet. This is another one of my favorite iconic images. This is Sunset on Mars, taken by Spirit. And it's evocative of not only the similarities between Earth and Mars, both have sunsets, they both share a common star, but also differences, because Mars is further from the sun, so you can see the disk of the sun is much smaller, and you can see that the sunsets are blue and the sky is pink, essentially opposite of Earth, with a blue sunset, pink sky, versus a blue sky and pink sunsets. But the rovers lasted long enough such that our next mission to Mars landed and began operating. And that is Curiosity, the Mars Science Laboratory. So where Spirit and Opportunity were field geologists for Mars, Curiosity is the analytical chemist for Mars. So taking the next step of exploration. Now you can see here in this image that it is a much larger rover, more capable, carries 10 times the instrumentation that Spirit and Opportunity carried. And it's also nuclear powered, so it didn't have the limitations of solar power that challenged Spirit and Opportunity. Since it will land on Mars using a different landing system, it didn't have those features in the wheels to mark off its traverses. So they deliberately added features to the wheels, and you can see here some holes in the wheels. Again, we were following the admonition of NASA this time not to put any JPL logos on the rover. So instead, the wheel hole patterns are Morse code for JPL. And so as the rover drives, it will imprint in Morse code JPL all along its traverse. So here's the landing system that it would use. It's called the Sky Crane. It's essentially a rover jetpack, if you will. It bolts over to the top of the rover. It propulsively flies close to the surface. And then in this artist rendering, it lowers the rover down to the surface to make contact. And when we landed on Mars, we had a worldwide interest in the landing. And so it landed very late at night in California. So it was very early in the morning. So this is in the wee hours of the morning in Times Square. And we're projecting the landing progress on the Jumbotron screens in Times Square. And the public was just enthralled with this. And so this was just an exciting experience to share, not just with the scientists and engineers that do these missions, but the public at large from around the world. So here is another selfie, this time of Curiosity, taken by its color camera at the end of its robotic arm. And if you see down in the foreground in the front of the rover, the rover has collected a few scoops of soil. One of the significant instruments among many instruments on Curiosity is a mass spectrometer, surface analysis at Mars, or SAM instrument. And it can measure the elemental and isotopic composition of whatever rocks or soil you can put into its sampling system. And so here it's now able to study the chemistry of Mars in exquisite detail. And so now it can look for complex compounds, such as complex organic compounds. So taking the next step in exploration. Spirit and Opportunity established the physical habitability of Mars. In other words, there was at one time temperatures and physical conditions that were conducive to life, at least life if we understand it. There was liquid water on the surface, there was a thicker atmosphere, there were warmer temperatures, and there were even sources of energy, hydrothermal or volcanic sources of energy that could drive an ecosystem. Curiosity was able to establish that there were the organic building blocks that are necessary for life as we know it. And so it moved us the next step towards establishing whether Mars could have supported life, or did support life, or supports life today. So we have all these ingredients, physical habitability, and now the chemical inventory, or chemical building blocks, if you will, of being able to support life. But we still haven't discovered whether there was life or is life on Mars. This is an image taken by Curiosity. This is of some broken pavement, and I think everyone on this Luncheon Society VideoCon will think, oh, that's a broken piece of sidewalk concrete that I trip over every day going to my favorite coffee klatch. And it is very reminiscent of that, because it is materials that clearly were formed and altered in an aqueous environment. You have the rounded pebbles that occur when you have abundant flowing water to polish them into round surfaces. Then you have the cemented rock matrix with those same rounded stones embedded into them. So clearly Mars had a robust liquid water history in its past, and very reminiscent of the early history of the Earth. And here you can see some samples that had a coring device to take powdered samples and introduce them into the instrumentation, some of which I've mentioned. Also notice the color change as these fine tailings, the grindings of the boreholes indicate what a geologist would call essentially a scratch test, that changing the color as you scratch or alter the material, indicative of its composition. So Curiosity is still running today. It was designed for a Martian year, just about 2 Earth years, but of course it has exceeded that, and it exceeded its distance. And this map shows where it landed way up here at the top at the Bradbury landing site, and has driven along the edge of Mount Sharp in the middle of Gale Crater, and is now ascending up the sides of Gale Crater. And much like any of us would be climbing a mountain, there are switchbacks. We go up to gain an elevation, but there's some exciting geology ahead of it. You can see in the symmetry, these valleys are putative flow channels that likely contain a rich history of the past on Mars. But we continue to explore Mars, and I've been focusing on the robotic vehicles. My apologies to my lander colleagues for not talking about their missions. But there is so much to talk about Mars, and now we have Perseverance. Approximately the same size as Curiosity, built on the same chassis, but different wheels. Notice no Morse code on the wheels. A different set of instrumentation, an improved set of instrumentation to explore Mars. But etched inside the wheels is some more iconography. And this one is suggestive of a Perseverance mission. You have one of the icons is of the wheel tracks that Perseverance will leave as it drives on the surface of Mars. But next to it, you see the characteristic double helix of DNA. What we want to do and are doing with Perseverance is to collect samples, intelligently identified and curated samples for eventual return to Earth, for sample return. So Perseverance has that instrumentation to decide where and what to extract into samples and to bring back, and to see if we can find evidence of current or past life on Mars. But it also carries a technology demonstration mission, and that is the Ingenuity helicopter. You can see it here. It has a dual rotor configuration. The rotors are, I think, about 1.2 meters in diameter. The whole vehicle weighs about 2 kilograms, just over 4 pounds. It's solar powered. That's a small solar array on the top of it. And then it will sit on the surface. It'll take a day or two to charge up its batteries, and then it will take flight for a few minutes. There are 2 camera systems on this, one that looks straight down and then another one that looks to the side. And this will change our perspective yet again on the exploration of Mars. But this mission is significant because this will be the first time we as a human species have ever taken flight on another world. And so in sort of, in honor of that significance, NASA got permission from the Smithsonian to have a small sample of the original Wright Flyer fabric. And this is a small piece of material, a couple centimeters on a side, that was taken from the Wright Flyer in the Smithsonian and put into the Ingenuity helicopter. The helicopter is affixed to the bottom of the rover. So here's Perseverance, and you can see that the helicopter is folded up and attached to the bottom. It'll have a safety cover over it. The final integration and assembly and testing of Perseverance and Ingenuity occurred during the height of the pandemic, when most of the personnel at JPL were sent home. Many vendors had to shut down, and it greatly restricted our ability to do our work. But yet we persevered, if you will, and were able to deliver Perseverance to the launch pad. But realizing that the work we did was enabled by the critical work that so many other people did during the pandemic, that we commissioned this little plaque, more iconography. And it shows the classic symbol of the healthcare profession, which is the serpent around the staff. But that staff is holding up the earth. And this is an acknowledgement of all the first responders, the medical personnel, the frontline workers, the essential workers who did their job at risk to allow things to continue. And the trajectory around the globe is the departure trajectory of Perseverance on its way to the planet Mars. And this was affixed to the rover. So here again is at the underside of the rover just before it was sealed up. And you can see the plaque here on the left side of the rover towards the rear. You can now see the safety cover over the Ingenuity helicopter. And then here is July 2020, July 30th, 2020, a safe and successful launch of Perseverance to Mars. And it's a 6-month trip around the solar system to arrive on February 18th to land on Mars. And this is where Perseverance is going. This is a photograph of the edge of Jezero crater, so a large, roughly 100-mile diameter crater. But you could see this dramatic flow channel that entered into the crater, and this really wonderfully preserved river delta that represents, much of the water history of Jezero crater. And this is where Perseverance has landed just to the east of this site. So one of the great things is they installed the equivalent of GoPro cameras on the lander and sky crane. And so this is a photograph of the parachute of Perseverance as it's traveling through the atmosphere of Mars towards the surface. And it has been annotated because the pattern in the parachute, which those of you who work in the aerospace community know we call a roll pattern. You put a distinct pattern in your parachute or on the side of your rocket that allows you to tell how it's rotated during its function. But the pattern was a binary code, and the binary code spells out, as annotated here, "Dare mighty things," which is a part of a quote from Theodore Roosevelt, which has become sort of an unofficial motto for JPL. And then around the periphery are some latitude, longitude coordinates, and then the latitude and longitude for JPL. So we didn't put a logo on the rover. We didn't put Morse code anywhere, but we did put a binary code in the parachute that is a deference to JPL. So there's only so much you can tell spirited scientists and engineers to do or not to do. And here is the camera looking down. If you haven't seen the video, I do encourage you to go to the NASA website or to YouTube and look it up. It's a dramatic video. It doesn't play very well over Zoom, so I refrained here. But you can see that the rover is descending towards the surface. You can see the swirling and the flow patterns from the thrusters of the sky crane as they blast the surface as the rover is descending down. And here we are on the surface several days after landing when we're deploying the Ingenuity helicopter. So we've dropped away the cover shield. We've driven away from that point. The helicopter is actually still attached to the underside of the rover, because you can see that the legs of the helicopter haven't actually touched down, but then there's a final release and it drops to the surface. And here is the helicopter on the surface of Mars, waiting to take its first flight. So its solar panel is charging its batteries on board. And then here we are on April 19th of this year. This is a photograph taken by the down-looking camera, which is a black and white camera, of the helicopter's shadow as it lifts off from the surface of Mars for the very first time taking flight on another world. So this is our Kitty Hawk moment for outer space. And then here is Perseverance using its cameras to image that first flight of the Ingenuity helicopter on the surface of Mars. And I mentioned that it has another side-looking camera, and it's a color camera. And so this is a later shot of from one of its later flights. And this really shows the power and perspective of a helicopter, an aerial vehicle for exploration. And this is yet again changing our perspective view of Mars. And you can just really get a sense that you are flying along with this vehicle and you're staring out over the Martian landscape and getting this tremendous perspective, which is really a great asset for exploration, because now the helicopter can provide instruction to where the rover can explore. This is not unlike we use drones for exploration now here on the Earth, or the military uses aerial vehicles for reconnaissance in military operations. In this image, if you look up over to the left, you can actually see the Perseverance rover on the surface of Mars. So this has been and will be a powerful tool in facilitating the exploration by Perseverance, but also pathfinds future explorations. So it's not hard not to think that going forward that this will be the type of technology we'll use in exploring worlds throughout our solar system. But just as any flight vehicle, you keep a flight log, and this is the flight log for Ingenuity. We have a pilot that logs each and every flight that the vehicle has taken. Since the Perseverance landed a little over 200 days ago, this is the path of both the rover and the helicopter. So the white trace is the rover as it's making its way roughly to the west, to the left side of this image, to begin to explore parts of the river delta of Jezero crater. The yellow line that moves in straight segments is the helicopter, and how it has explored and sort of followed the trajectory or led the trajectory of the rover in its exploration. I believe it's taken 13 flights today. As of right now, we're in a period called solar conjunction, where Mars, as viewed from the Earth, is very close to the line of the sun, and that we can't communicate reliably or listen to the vehicles when we're that close. So we're in a period of operational stand down for all our Mars assets. We're just about to come out of solar conjunction, and so we expect the resumption of the exploration of Mars any day now. So here is a selfie taken by Perseverance of herself. But you can see in the foreground a rock in which there two cores had been made. So these are the first core samples that Perseverance have made. And this is significant because this is the first in the series of samples that will eventually be returned to Earth. So where Curiosity could make powdered samples to put into its instrumentation, Curiosity can actually extract solid cores. They're about the size of a piece of classroom chalk. And they get sealed into these containers. Excuse me, there we go. Sealed into these containers about the size of a cigar tube, and they're hermetically sealed. And that as Perseverance explores, it will collect up a set of these, which will then be left on the surface for later retrieval. And this is part of a larger undertaking of sample return that's indicated by this graphic. So on the left, you have the Perseverance rover. In the center, you have a small fetch rover, which will be sent to Mars with the landing system that you see on the right. The fetch rovers will retrieve those core samples from the ground that will be deposited by Perseverance, and then return them to the lander and install them into a launch vehicle. You can see a little hatch open here and a carousel in which those individual samples will be inserted. This will then be closed up, and the lander will then launch a small rocket, a Mars ascent vehicle, to launch those samples into orbit. And then they will stay in orbit until they're rendezvoused by an orbiting spacecraft. And this spacecraft will synchronize and sync up with those samples, and then eventually deorbit from Mars and return to Earth. And what you see here are the samples being released for ballistic return to the surface of the Earth, where those samples can then be retrieved. Why do we want to do sample return? Well, the great advantage of sample return is that we can then apply all the analytical capabilities on this that we have here on the surface of the Earth to studying those samples. You know, the Apollo rock samples we brought back from the moon are still being studied. And much of the instrumentation we're studying those samples with was not invented at the time the samples came back from Mars. So there is instrumentation yet to be invented that can be used and will be used to study these samples once they're returned, something of the order of the next decade or so. So I talked about the rovers at Mars, but I didn't talk much about the orbiters or the other missions at Mars. So I'll sort of conclude with this snapshot. This is a graphic tool that you can download from the web that shows the current activity at Mars. And this is just a few days ago. And it shows all the things that are going on at the red planet. You have, here is M20 is Perseverance, the Mars 2020 rover on the surface. Over here is the InSight mission. And here's the Mars Science Laboratory, Curiosity. And then the orbiting spacecraft, you have the Mars Reconnaissance Orbiter, you have Mars Odyssey, you have Mars Express, and you have the European Trace Gas Orbiter mission that are in orbit. And not shown on here, it's not in the field of view, is the United Arab Emirates Hope mission, and then the Chinese Taiwan 1 Mars mission, and their rover on the surface of Mars. So it is a crowded place. In fact, there's a traffic jam of activity at Mars. And this is just a harbinger of the sustained activity of the exploration of Mars going forward from here. So I will stop at this point and allow you to ask any questions or offer any comments you like.
Okay, so what we're going to do, this is great. This talk about a great tee up for what's going on in Mars. So what we normally do is this: put your name into the chat section, just your name. You don't have to put your question, and that'll form as our cue. The first question I have is this, and I've asked this one before, but it bears repeating. Exploration comes with a series of happy accidents. And one of the happy accidents that was either on Spirit or Opportunity is that one of the wheels froze. But as a result of that frozen wheel, something came of it. And I'm going to tee it back to you, John.
Okay, yeah, thanks for that leading question. Yeah, this might have happened to any of you, that you're taking a trip with your family and the car's loaded with the kids and all the vacation stuff, and you're trying to get to a destination, and somewhere along the way you get a flat tire or the car breaks down, the radiator leaks, and you're stuck in a small little town that you never expected, and so you have to spend the night there while you wait for AAA or whatever, and you end up having a wonderful experience as a result, and an unexplained experience. Well, that kind of thing happened with the Spirit rover, that the right front wheel failed. It lasted much longer than it was designed to do. And because these wheels have a very high gear reduction, it's a 1501 gear reduction, the wheel won't spin once the motor fails. So it's kind of locked in place. In fact, that's part of the design, such that you turn off the power and the rover doesn't roll away on you. And so we had to drag that wheel. We could power the remaining 5 wheels, and we still had reasonable mobility, but we would cut a furrow in the ground as we would drag that wheel behind us. Well, as a result, it unearthed what was just beneath the surface at a couple of locations. And one of those was the presence of opaline silica, which is amorphous silica formed in water, but formed in hot water, a hydrothermal system. So this allowed the discovery of hydrothermal systems on Mars, which was unexpected. It was unplanned, I should say. And that was one of the significant discoveries, because it showed both the presence of water and the presence of an energy source. And any of you know, here on the Earth, wherever you have the two, water and energy, you have a thriving ecosystems, whether the geysers of Yellowstone or deep ocean volcanic vents. So yes, that was one of the serendipitous discoveries that came about as a result of a happy accident.
Okay, we'll start with Jill Tarter. Jill, you're up. And you're on mute.
Yeah. So, John, is there any consensus about methane and the origins?
Oh, I might even defer that to David DeMarais, but I'll give some comment. So yeah, there's been suggestions of the presence of methane on Mars for some time, first with ground-based observations, and then more recently with both, particularly with the Curiosity, because the mass spectrometer can also ingest atmosphere into it, and have found traces of methane. So there is methane. I don't actually have the latest on what the consensus is. I don't know. Dave, can I put you on the spot and see if you could offer anything?
I think, Dave, you may be on mute, so go ahead.
Dave DeMarais, yeah.
Yes.
Yeah, I'm hopefully unmuted.
Yeah, we can hear you.
Yeah, we can hear you.
Well, I think one of the challenges was that you would detect the methane in the atmosphere either with the orbiter or the lander, and then it would just go away. And the physicists use a polite term for this, and that is that this just fast disappearance is non-physical. In other words, there's not enough things that could bump into the methane chemically to destroy it. because of the thinness of the atmosphere and the availability of the things that would destroy methane in the atmosphere. And so the non-physical is just a polite way of saying we don't believe this. But what's becoming more obvious is that it seems to depend on wind direction when it's detected by the Curiosity rover. And if you thought of methane as maybe having a point source on the surface someplace, and now you see it, now you don't, just simply due to wind direction, that it could be consistently consistent evidence of some sort. So it always makes the point that whenever you're observing something in the atmosphere or wherever, you really need to document all the conditions surrounding that. And if we can end up over time determining that when the wind's coming from a certain direction, that's when we see the methane, then that would really strengthen the evidence. But yeah, it's still sort of a TBD, but the people who do the measurement on the ground really do believe in those numbers. And it took them a while to get it firmed up. But so that's where we are. It'd be very exciting because methane doesn't necessarily indicate life, but it does indicate the chemical activity of liquid water. You sort of need liquid water to make methane, even in a hydrothermal system or deep within the earth. And so it would be exciting. It would mean that somewhere in the subsurface, we have water with enough activity that it could, in principle, support life down there. So it's something that we'll continue to pursue.
And I'm going to actually bring Jerry Ostreicher to the front of the line here because he had a follow-up. And Jerry, go ahead.
You're muted, Jerry.
Jerry, you're muted.
I was wondering whether you could do any isotope ratios from your mass spectrometer. For example, if you have carbon, because as you know, that can be a sign of processing, including of life.
Yes, you can. The SAM instrument does have that, and they've done isotopic ratios, and they've been looking at some very important ones like the deuterium to hydrogen ratio. But once again, maybe I'll put Dave on the spot because Dave's on the Curiosity science team. That they have done some very significant isotopic measurements that tell us something about the past. Dave?
Yeah, there's two challenges. One is that on the Earth, when we see methane having a certain value, we've got a wonderful reference point in terms of the water in the ocean and all these other, and where carbon is in the rocks and everything. And that gives us a reference point to say, boy, if the number is a certain range, it must be biologic. We don't have that yet for Mars. We've got to do a lot more analyses. We've got more of a sense of what the total isotopic inventory of Mars is, and that's just TBD. The other thing is there's a major process on Mars that's not so important on the Earth, and that's escape of gases into the atmosphere. And on where we do document that on the Earth, there's a big isotope effect. And just with the destruction of a gas like methane in the atmosphere plays around with the isotopes. So it's methane, it's part of a system. And you just have to understand all the gears in the machinery before you can make an interpretation. So it's just further motivation to keep studying Mars at a sort of a global context.
Okay, so we have Karen Mitchoff, Liz Kennick, John Manulis. Karen, you're up.
Hi, thanks, Bob. Sort of a narcissistic question. How do you get your name or your signature on one of those chips? Does it cost money? I'm assuming it does.
No. You just have to wait for the next mission and they'll open a web page. So all it required was just going online to the NASA website and clicking on the link that says send your name to Mars and add your name. So sorry that you missed the last
No, that's
but,
okay.
but stay tuned for the next one.
Do they announce it or you just got to know to go?
No, they do announce it because they actually tried. So for Perseverance, I think the number was close to 12 million signatures from around the world were sent to Mars.
Well, and a follow-up a little bit different. I'm just so I don't know why I'm surprised, the creativity and everything there, but I'm thinking more that iconography. Is there a special department at JPL that sits there and figures out what to do, or everybody's just around the coffee pot going, this time let's do this?
It's we do have a special team for stuff, but they haven't been involved in the things that I've mentioned in today's presentation. No, it's more, someone has a clever idea and maybe they tell someone, or maybe they don't, and they just do it. And, and there it is. So, like the roll pattern for, someone had to lay out the pattern for the parachute. And, so some person chose a parachute, but other people didn't know that it was a binary code that said something.
I just think it's fabulous. Thank you so much for your presentation.
All right,
You're
Liz
welcome.
Kinnick. Liz, you're up, then John, then Brad. Brad Zamanian. Liz, you're up.
Yay, thank you. This is so great. What a fantastic presentation. I wish that we could have this presentation at every workshop that Teachers in Space does for teachers. Our focus is teaching teachers things they can do to help bring space into their classrooms while also getting them ready to go to space themselves. We've been focused on remote sensing, data collection and presentation, satellite communications, and we're launching our first educational satellite. But as we move toward actually being able to get teachers to space and in preparation for their students growing up to work on Mars missions, can you tell me, are there any areas that you really think we should be focusing on right now to help teachers bring the reality of Mars exploration and science and eventual human missions into their classroom, especially at the high school level today?
Well, Liz, maybe I'll go ahead and make an offer right here that I'm an adjunct faculty member at the local community college, and I love bringing this stuff into the classroom, and they just eat it up.
Yeah.
And so, Bob, if you want to forward my email
I'll make
to
sure.
Liz, we can follow up. But yeah, it is, for me, it's easy to talk about this stuff. I mean, all of you can take my pictures and give a great talk too, because the content sells itself.
Yeah.
And it's a great story because it's a story of exploration and discovery, of solving hard problems, and how you use your own innovation and your own critical thinking to solve these problems, and how you cannot fake the real world. The reality of the physical world will prove whether you are right or wrong, one way or another. And those are all powerful lessons to learn. Speaking for myself, but I think, Dave DeMarais and Mike Werner, my colleagues, would say that, in this field, it's lifelong learning. We constantly learn stuff every day, all the time. And that's also a powerful message to bring into the classroom. It doesn't stop at graduation. It shouldn't stop at graduation. So taking those messages forward, lifelong learning, solve the hard problems. I say this to young groups. I say anyone can write another social networking app or develop a new gig economy business, but the problems we really need to solve are things like climate change and how to solve the nuclear weapons threat and live in peace with each other. Those are the hard problems that we really need to solve.
Thank you.
John Manlius, you're up.
Hi, thanks. I'm just curious because obviously for understandable reasons, there's tremendous focus on groundwater. I mean, on surface water and the history of that. And I'm curious if we have any ability to investigate groundwater.
Yeah, great question. Because today on Mars, the atmosphere is too thin to support liquid water on its surface. Be either an ice or a vapor. But there is some suggestion and some arguments that said that there could be subsurface liquid water on Mars today. There could be aquifers. And we do have some ability, and that is with radar penetrators that can penetrate through the surface. So the orbiting spacecraft have some of that capability and can do subsurface sounding. And they do see, things that are suggestive of ice layers. Then there is the question of drilling on Mars, and that would be a very exciting thing for future missions. And I actually am not up to date to where the Europeans have an ExoMars mission, which would be their rover. And I don't know, Dave, do you know, does it still have the coring system designed for it? I think they were designing a multi-meter drilling system for the ExoMars rover.
Yeah, the philosophy there is that they'd like to get down about 2 meters or so. And the significance of that is that we're interested in looking for organic matter and other kinds of remnants of life, but the cosmic radiation on Mars is pretty nasty to that stuff. But they've calculated that you can calculate that if you can get about 1 to 2 meters beneath the surface, the destruction of that is greatly reduced. So they pretty much have designed to specs in terms of what they think, how far they need to go to get something that's better preserved.
Thanks, Dave. Yeah, but it's a challenge to robotically drill. But there are teams that are looking at even deeper systems, future missions that might contain a deeper drilling system to do the kind of things that Dave mentioned and the kind of things you suggest about looking for groundwater.
And I'm going to jump in for a question before we move on to Brad. And it really goes to, again, NASA playing the long game when it goes to, when it starts off with small robotics, it goes to complex robotics, and then potentially a manned flight. I want to bring Doran into the conversation as well on this one, as because he's the only person on this call who's orbited the Earth as a cosmonaut. I want to get his thoughts too about how feasible a Mars flight is. It's far more complex than obviously a trip to the moon. And when we had head of mission control, I can't remember his name.
Chris Kraft.
Yeah, when we Chris Kraft, we had him. He joined us about 10, 15 years ago. And he was talking about how Mars would be the outer edge of manned flight for the near term, perhaps the far term. And I want to get an idea if that's real, if the human condition can push itself to Mars and beyond. And I'd love to hear from both John and Doran on this.
Okay, well, we have the technology to do this, and that is it's all about speed. Some of the scenarios they talk about sending humans to Mars is that you first send a solar or electric powered cargo vehicle, which can take its time to get to Mars and get into orbit around Mars, and it carries the surface landing assets as well as the return vehicle. And then you send a smaller, perhaps nuclear thermal powered vehicle that carries the humans. And so it could make a faster trip to Mars. But as I'm sure Doran will say that, in the weightlessness environment of space travel, the human physiology degrades and it's challenging. And it's, even though they exercise, they exercise hours a day, the astronauts, the cosmonauts, they still can't mitigate the bone mass loss, the muscle loss, and the other effects. And so what we want is for our astronauts and cosmonauts to be healthy when they arrive at Mars and can explore, and we want them to be healthy, and return safely to Earth. There's also the other risk that once we get out of the Earth's magnetic field, as the Apollo astronauts would be experience, is that they are no longer protected by that magnetic field. And if there was a large solar mass ejection, a coronal mass ejection, that could potentially be lethal to astronauts and cosmonauts. And so we need to have a system in which we can shield them during their flight. And, and people talk about things like you put a special bunker inside the center of the propellant tanks of the vehicle, such that the astronauts, cosmonauts would sequester in there, having all the rocket propellant around them to shield them against the subatomic particles, mainly energetic protons, from a coronal mass ejection. So,
Doran, what
really
are your
like in
thoughts?
space.
Yeah. Thank you, Bob. Very, very interesting presentation. Thank you, John. I was unable to see it from the very beginning, but I'm sure I can see
I'll
the
take care of
recording.
that. Don't worry about that.
Yes, thank you very much. Thank you very much. It's really difficult to fly into space. It's much more difficult to fly on the moon, but it looks not impossible, but close to impossible to fly to Mars now for humans. Of course, as John said, there are so many problems connected with the health of astronauts, with the physiological processes in the body. A flight to Mars and back could take maybe 2.5, 3 years, working on Mars several months. And it's a real challenge for the humans to do it. I'm very curious how we'll develop the Artemis program and the exploration of the moon, the permanent base on the south pole of the moon, and what experiences the humanity and the scientific community will learn from this endeavor. And of course, it will serve as a starting point for a flight to Mars. I hope I will live that time when human colony on Mars will be settled and to see what happened. I'm very curious from this point of view, having my own experience of flying into space. So I did it only for 8 days, but I see now the astronauts fly much longer. Normal flight, usual one, it's half a year. There are astronauts that fly close to 1 year into space, learning on their own body what means weightlessness and so long time spent into the outer space. Okay, in any case, I continue to follow your discussion. It's very, very interesting. And it's very important for me also, not only for my knowledge, but for delivering such information to the students. Because I have many meetings with students in the high schools, in the universities, and also in the summertime here in Romania, we organize camp for teaching the teachers of science. And such information is very important, not only very interesting, but very important to be delivered to them. And presented by a specialist directly involved in these activities, it's the first source of information for us, for me, for my friends. Thank you very much.
That's great. In fact, I'll make sure that, Darren, I'll make sure that I connect you to Liz as well. So there might be a good opportunity. One more thing before I go on here to the next question. It's just a point of personal privilege. Because I've collected stamps for 45 years and have a pretty good Romanian collection, I do have the stamp that celebrates Darren's flight on into space.
So I celebrate this May, I celebrate 40 years from my space flight, and we have a special issue, a philatelic issue. Okay, keep in touch, keep in touch.
I'll be in touch with you soon. Okay, Brad, you got the next question.
Okay, thank you so much, John, for the presentation today. My question was, bringing back a sample from the surface of Mars sounds like a really, really expensive endeavor. Is there not a more cost-effective way to kind of thoroughly analyze these samples on the surface?
Great question, Brad. Yeah, I mean, this is the debate that we had is, why not just develop the instrumentation you need to study the samples and send that to Mars and just study them right there, today. Well, we do have a lot of great instrumentation on these landers, on these rovers. The SAM instrument on Curiosity, and there's for example, there's a Raman, very capable Raman spectrometer on Perseverance. But there are limitations to what you can send. I mean, if you walk into a high-end analytical laboratory today, it is a large room filled with very sophisticated big systems to study really tiny samples. And as I mentioned, there's instrumentation that we haven't yet invented that we would be able to bring to bear. So again, I go back to the analogy with returning the Apollo samples, is if we tried to study the lunar rocks with what instrumentation the astronauts could have carried to the moon at that time, we know much less about the moon than we do today. So in a sense, we're kind of future-proofing the exploration of Mars by bringing a piece of Mars to Earth. Now, there's also an argument that says, well, we have samples of Mars already in the Earth, the Martian meteorites, and those are being studied in great detail. The problem there is we don't know the context in which those samples were thrown into space. And here we can carefully document when we take a sample, when Perseverance takes a sample, they've they've documented the site. We know where on Mars, we know what rock, we know the context that rock was in, we know what the rock matrix was like, we know, we have imagery of the sample. So we have a tremendous amount of contextual information, which is an essential part of doing the interpretation of the samples once they come back. But it really comes down to being able to, do everything. It's not unlike something here on Earth. You have a service person coming to your house to fix something, and they have tools in their truck, and they get to the house. Well, I don't have the part for it, or I don't have the tool for it, or it needs a different tool. And they take your item that needs to be fixed and they bring it back to the factory, and they service it there and then return it back to you. So, a little bit of an analogy there as well.
Quick comment I'd like to make right there, and that is sample preparation. Something as simple as slicing a rock into a thin layer so you can look through it with a microscope is really hard to do on a mission. We'd love to be able to get thin sections of stuff. And the preparation can be quite sophisticated to enable the full capability of those big instruments you're talking about.
Thanks, Dave.
Okay, next we go to Jim Brosnahan. And Karen, I don't know if Karen, you had a second question. You'd be second. Then we would go to Pat O'Brien. So Jim, you're up.
Thank you. Wonderful presentation. My question was about human flight, and that's been pretty well answered. But if you had to guess, even as to a range of time, when would you guess that humans would get to Mars?
Well, the NASA answer is, in the next 3 decades. But the reality may be that someone else may get there first, that private industry. Elon Musk has said several times that he intends to go to Mars. He would like to go to Mars. Yeah. I'd like to send him to Mars. It could be that a private undertaking, whether it's SpaceX or Blue Origin or High Sierra or some other innovative company or privately financed operation, can send the first human team to Mars. Or it may be, maybe the more likely will be a international collaboration between the international space agencies and private industry to make this happen, and make it happen sooner rather than later.
Mm-hmm. Thank you.
And next, I think we have Karen. Karen, did you have a second question? Then we move on to Pat O'Brien.
Yes, thanks. I've always been interested in Mars since I was a kid and read Arthur C. Clarke's Sands of Mars. So just a fantasy book, but one that got me started. I had a question on a helicopter. They obviously, with a thin atmosphere and on Mars as compared to Earth, the aerodynamics are going to be different. So what kind of calculations or thought processes went into engineering such a fantastic vehicle?
Sure, great question. As you might expect for any flight vehicle, a lot of analysis, a lot of simulation, and a lot of wind tunnel testing. And the challenge with Mars, as you point out, is that the atmosphere is only about 1/70th of the Earth's atmosphere, a little over 1% of the Earth's atmosphere. And so in order to generate the same amount of lift relative to the Earth's atmosphere, the rotor blades would have to, spin. It goes as the square of the rotor speed. So the rotors have to spin somewhere around, I think it's 6 times faster than a traditional helicopter. So they're going several thousand RPM as opposed to a few hundred RPM. The one advantage we have with Mars is the gravity is lower, so you don't need as much lift. It's about 3/8 of the Earth's gravity. So I think the rotor speed is something around 2,400 RPMs, whereas a typical Earth drone spins at about like 400 RPMs. So that's the main way to do it. And we did test this. We have a large chamber JPL that we put down to Martian atmospheric pressure. and then using different ways of unballasting the vehicle, we could simulate the flight of the vehicle and study its stability. We do have to worry about things like the wind. So, you don't want to fly this thing in a strong wind, much like, trying to fly a kite when it's too windy or too turbulent.
Allison, you're next.
Thank you, Bob. John, that was really interesting, and I appreciate your keeping it simple enough that a U.S. history degree was sufficient to follow you. But another probably dumb question, if I understood you correctly, you said you needed an atmosphere for water to flow. So I'm wondering what happened to Mars. Do you know what happened to Mars' atmosphere, and can that happen to Earth?
Great questions, and I often give talks where I lead in with that very question. If you remember your phase diagram for water from high school chemistry, I know it's a long time ago, but below a certain atmospheric pressure, water can no longer be a liquid. If you get below what's called the triple point of water, it's no longer a liquid. It's either a vapor or an ice. And so on Mars today, the atmospheric pressure is below that point, and so it can't be a liquid. You need a thicker atmosphere. So that says that Mars must have had a thicker atmosphere if we had physical evidence of sustained liquid water flow on Mars. So what happened to the Martian atmosphere? Well, we don't know, but we have some ideas, and they range sort of two different groups. One is that the atmosphere was lost to space. We see evidence of an ancient magnetic field at Mars. That might have been powered by a dynamo of the circulating core, much like the Earth's molten core circulating produces a magnetic dynamo, it gives us our magnetic field. Our magnetic field at the Earth protects us from the ravages of the solar wind of the sun. Without the magnetic field, you literally can blow the atmosphere off a planet, much like you take a dandelion seed pod and blow all the seeds off with it. It takes of the order of 1 billion years, you can blow away the Earth's atmosphere with a solar wind. So maybe that happened to Mars. Without that atmosphere, the water's not a liquid, but furthermore, the ultraviolet radiation from the sun is more intense now at the surface, which can break liquid water down into hydrogen and oxygen. Hydrogen being a very light element, drifts off into space, escapes from Mars, literally. The oxygen can bind with surface minerals. That's why we see strong evidence of a highly oxidated surface mineralogy. Another possibility is the atmosphere, which was thought to be mainly carbon dioxide, dissolved in the ocean. Our Earth's ancient carbon dioxide atmosphere dissolved in our ocean, precipitating out as carbonate minerals. And we know it today as the chalk back when they had chalk in the classrooms. That calcium carbonate is the part of the ancient remnant of the Earth's CO2 atmosphere. So losing it to space, or dissolving it in the ocean, or something else. And part of why we want to continue exploring Mars.
Okay, Jill Charter, you're up next.
Yeah, going back to the discussion of humans in Mars, both NASA and ESA go to great lengths and expense to abide by the COSPAR planetary protection rules. Do we have any sense of whether the private sector is willing to take on that mantle and that obligation?
It's a great question, Jill, and it's probably really sort of outside my wheelhouse to comment on that. I will mention something else that's of great concern to the scientific community, and that is the launch of numerous Earth orbiting satellites to provide worldwide internet communication, because for astronomers to suddenly have to stare through this ever moving field of false stars across your camera lens really will compromise our ability to do deep space astronomy. And similarly, the rollout of 5G terrestrial communication, the radio frequencies they're using for that fall right next to the very critical water band that the NOAA weather satellites use to track, moisture in the Earth's atmosphere for weather prediction. And we really stand the risk of becoming blind to that information and losing critical observational capabilities of the Earth. So industry has to be a partner along with these international scientific agencies to understand that it's a precious resource. Preserving the biological pristineness of Mars, or the ability to view stars in the sky, or to be able to monitor the weather. Yeah, are all things, it's, an environmental question, and we need to be good stewards of that precious environment.
I'll jump in and ask the next question. We'll pivot a bit from science to how science is portrayed through the lens of entertainment. And I'll open this one up to Jill. As many of you know, Jill was the fictional base that Jodie Foster's role in Contact was derived from. And also too, when you look at other space movies, not only ones that we're used to on the American side, like Apollo 13, but there's also a very good Russian movie made on Alexei Leonov, and it's fully subtitled. You can find it on YouTube. It's about Bakshad 2, all that it went through. So I'll open this one up to Doran as well as Jill and John. What do the movies get right, and what do they not get right? John, go for it.
Oh, wow. Okay. Yeah. Well, you're asking the wrong person, because I've been often very critical.
I know, it makes it great.
But it's like, anything. If you have a particular expertise, and you go to see a movie that showcases that expertise, you're out of your seat with criticism of what they're doing on the big screen. My brother is, a retired Navy captain, and anytime we see a contemporary military movie, he just shakes his head and says, "Oh my God, no way, no one acts like that," or that's not how it would be done. And so, I have that same challenge. I had to do an interview with Andy Weir about the movie The Martian, and I was really biting my lip the whole time during that interview, because I just wanted to rant incessantly about all the things that were there's a certain artistic license that we understand that you have to take to tell a story, but when they ignore the real story, which is real life is often so much more exciting than fiction. And they put in a lame fictional substitution for it, then those of us that know the reality are disappointed by that. So I'll leave it at that and let
Doran, what are your thoughts?
Yeah.
And the Leonov movie was actually pretty good. I'm guessing it hewed close to reality, because I know that I'm just, the published report said they had problems at the get-go with Leonov trying to get him back into the into Bakshad. He nearly died. There's all sorts of crazy things that went on. But I'll let you answer the question too. Go ahead. You're on mute.
I'm muted. Yes. Actually, I've seen the movie with Leonov. I've seen other movies made by the Russians connected with the space flights. They really did 3 good movies. That one with Leonov, the first EVA, another one with the Gagarin team, how Gagarin was selected and how he flew into space, and another one about the loss of Salyut 7, when a crew came and reactivated completely the space station. So the most non-realistic one was the last one with Salyut 7. The realistic one was the one with Gagarin and Leonov, and the most dramatic one, of course, was Leonov's one. I had the opportunity to speak with him many times, and he explained us, including at the congresses of the Association of Space Explorers, all his experience with this first EVA, how he was close to die into space, how he released the pressure from the spacesuit to get inside the space craft. In any case, for that movie, Leonov was the advisor, and the movie was the most realistic one. I've seen The Martian. It looked pretty close to what could really happen on Mars. Of course, it's a fantasy, but I was so passionate. First, I read the book, and then I've seen the movie. And of course, having more details from the book, I understood much better all details from the movie. I was really impressed, and I really had the desire to continue to fly, maybe to fly on the moon or on Mars. I may be too old now to do it.
And the follow-up,
I'll be 70. But in any case, I'm very curious how all these things will develop in reality when a real person will fly on Mars.
before we go to Jill on that same question, two follow-ups. In the Leonov movie, did they get the Korolev character correct in terms of how he was? And the follow-up would, if Korolev would have lived, would Leonov landed on the moon?
Yeah, actually, in the movie, Leonov is as he was in reality, a tough guy who really did the job. He was not afraid to take that job and even do it with all risks, including of losing life in this space flight. Yeah, unfortunately, he died 2 years ago already, and we were good friends. And he was a good friend of all astronauts and cosmonauts. As you know, we together were two of the 25 founders of the Association of Space Explorers back to '85. And I and Leonov were the only ones taking part in all congresses of the Association of Space Explorers. Only once Leonov was not able to be present. We had a congress in the Czech Republic. He had a heart surgery at that time and was unable to do it. But in any other time, he was present, promoting all the time the international cooperation, friendship, cooperation between US and Russia and between other nationalities. Now we at European level encourage very much the cooperation with all nations in space field.
And Jill, you were portrayed, albeit fictionally, by Jodie Foster. Walk me through how that impacted you, not only you personally, but also SETI from a larger perspective.
Yeah, well, John Callas, I think it's worth biting your tongue because now Contact is old enough that I end up with university students saying to me, that was my favorite movie. That's why I went into science, right? So even though when Jodie Foster does the equivalent of the Drake equation and ends up taking 10 to the 11, multiplying it by 10 to the minus 18 and coming up with 10 to the 6, and you want to go, that's so wrong. It's still worthwhile. It does give, I mean, you can't imagine being what you can't see. So giving particularly young women a role model to think about STEM careers, I think that entertainment plays a big and positive role that way.
And is there truth to the rumor that there's a sequel in the works?
Yeah, Ann Druyan says she's working on it. So someday, maybe we'll have another.
There you go. Well, I think we got time for one more question. We're going to wrap things up. This has been fantastic. Is there somebody who hasn't asked a question who wishes to raise their hand and get the last piece of pie? Nobody? Oh my goodness. I'm going to pick somebody out here. I'm going to put my niece on the spot. Oh, and Lisa, you're up.
I was going to ask, is it highly competitive? Like you said, John, that Emirates are, all these satellites are orbiting up there. Like it's really busy. Is it competitive or is it a cooperation effort?
Oh, it's very collaborative.
Okay.
Most of the spacecraft at Mars are taking advantage of the NASA Deep Space Network for communication and commanding. So the United Arab Emirates are part of that. Not the Chinese mission, but others are. And we share information. I mean, the European Space Agency and NASA work closely together. Scientific discoveries are the providence of everyone. And so, what we learn, one of the very important things you need to do is precise navigation in deep space. And, JPL produces these detailed ephemeris data that allows spacecraft to navigate accurately and safely. And the other thing is you don't want to have collisions. You think there's a lot of space in space, but it is, something you have to look at, because even though the probabilities are low, the consequences are catastrophic. And of course, it's much more of an issue for Earth orbiting systems. And that we always look to see what is overhead every time we launch a rocket, because we want to make sure we don't get collide with some space junk or a near Earth asteroid or something like that. So there is tremendous cooperation in space.
Thanks.
And with that, we're a few minutes into extra innings, but nonetheless, I want to thank John for a wonderful presentation on Mars. And I want to thank Jill, Darren, and David and others for great color commentary. Just a quick housekeeping. And Darren, Rusty sends his best. They are all in they're all at Johnson, the Johnson Center for the planning of I think Mike Collins's tree is today. So they're all down there. So they send their best. So with all that, I want to thank everybody for coming, and there's something fun coming up very soon, and we'll all be in touch. And until then, have a great day.
Thanks,
Thank you, everybody.
Thank you, Bob.
Bye-bye.
Thank you, John. Thanks,
Bye-bye now.
everybody. Bye-bye.
Where's the person?
Let's see. Still there? Where did everybody take off? Jill, at some point, maybe we can do a kind of an update on SETI or something like that as we go into the new year.
Happy to do that.
What now? There's talk about an updated Kepler. Is there talk? Am I missing something?
I'd have to look that up. I'm not
It just
aware
seems
of it.
that, I mean, if my math was correct, it's the Kepler's field of vision is basically a fist in the sky.
Yeah, it's 100 square degrees.
There's a lot of other.
But Tess has done the whole sky.
Oh, okay. I didn't know that.
Yeah.
And Doran, before you go, I wanted to ask you. No, the Leonov movie is great. I mean, it's great.
That was scary.
It was,
Really,
I mean, the opening shot where they've lost control of his jet, and he somehow lands it. But what I didn't realize until I watched the movie and then I did some reading afterwards was that they land. That's the good news. The bad news, they land in the middle of a storm.
Yeah, that's right.
The worst news is that you hear polar bears out in the distance. That's not good. And it's just amazing. And I mean, Korolev is a curious figure for me because he was shrouded in mystery by the Soviets. There's a great scene out of, I think, The Right Stuff, where they have this kind of fictionalized version of Korolev taking place every time there's a Soviet advance. And and then he got sick, and then I think that he had surgery that didn't go well. And then from that, the Soviet program seemed to falter a bit.
Yeah, just decreased. Yeah, that's right.
Because one of the people we were trying to get, and he just passed away, and I had a variety of conversations with him, was Sergei Khrushchev, who was
okay.
Obviously the son of the Soviet premier, but himself, I think he worked either under Korolev or had something to do. He was the upper echelons, but sadly he's passed, and we didn't have a chance to do that. But
yeah, I've seen some interviews with him connected with the old time, his father's time, and so on.
Well, the great story before I go, and when I would talk to him, I could understand every 4 words because he had a very strong Russian accent. It was hard to hear. And I asked him, how did you feel about how Western actors portrayed your father? And I mentioned, I mentioned the Missiles of October. There was Howard Da Silva, but he was okay. But what really got him upset was the fact that Bob Hoskins played his father in the movie Enemy at the Gates. He goes, I cannot countenance an Englishman portraying my father.
So I have a Leonov story at a Starmus festival in Tenerife. The stage was in a resort, and we had a series, a session with the cosmonauts and astronauts, and Leonov was there, and he went on longer than he was supposed to, and that stage was scheduled for flamingo dancers, right? And so Rusty is trying to shut down Leonov as the dancers are behind the curtain, getting more and more concerned as we run late and they can't get their stage act on.
I just remember him when we were all together in Berkeley that one time. He walked up to, I think, Bonnie Dunbar, who was a shuttle pilot who was up in Seattle. He goes, hiya, hot stuff.
He was great. He was really great. All right. Thank you for doing this, Bob.
Hey, it's good to see you. It was great, and we'll talk more. Folks, have a great day. Take care.
Thank you.
Bye-bye, Lauren.
Thank you, everybody.
Bye-bye, Jill.
Bye.